Hello LearnStem, we're back with another episode today. In this episode, we're going to be talking about gradients and their use cases, specifically Lagrange multipliers. I'm sorry if my voice sounds a little bit off for some reason, but that's because I have like a sore throat, and so I might sound a little bit off, but hopefully it's not going to be too bad. But with that out of the way, let's get into today's episode. Oh yeah, and just as a disclaimer, today's episode is going to be a lot heavy into math. So if you're not sure what is going on, make sure that you don't try to confuse yourself and get too frustrated trying to understand today's video, as it is a very high level math type of video. So hopefully you can stay with us and understand everything that is going on. But if not, feel free to come back another week. Okay, so before we get into a gradient and what it is, let's talk about a few specific things to know before we dive into that. So if you aren't familiar with calculus or whatever, we know that a derivative of a function is basically the slope of the tangent line. Well, it's the tangent line at a specific point on the function. It graphs the rate of change of the function in a 2D function. And it's always in respect to one variable in a 2D graph, whether that's x, y, or t, if it's parameterized. But in calculus 3, in multivariate calculus, we find the differential, or we derive the function, take the derivative of the function in a different way. As now it's not in just terms of x or y, now it's in terms of x, y, and maybe even z, if we're going for a 4D function. And when we try to do the derivative of a function, you can't always just, take the derivative of something in respect to x, because we have y's and z's. And if you're not familiar with how to, now differentiate a function, because it has multiple different variables, we have to derive it in different ways. Let's say we have a function of x and y, and its output is z. That means that we'll have to derive the function in respect to x, then z. This is what is known as the partial differential. For instance, if we have the function f of xy is equal to x squared plus y squared, then we know that we would need to partially differentiate in respect to x, which would be 2x, and then partially differentiate in respect to y, which would be 2y. Combining this together is what is known as a gradient. Like what we have already known in calculus, in just regular calculus, we now know both of the rates of change of the function. And combined together, we can get a tangent plane, or we can find the slope of the function at a given point on the line. But when we combine both of these functions together, we now have what is known as the gradient vector. If this does not make sense to you, like I said in the beginning, feel free to check back on my other video, which is all of physics and calculus. In one video, while it doesn't cover everything like the title says, it'll give you a good understanding of what I'm talking about, and it will go a lot more in depth into specific use cases, solve problems and stuff like that. And if that still doesn't make sense, keep on learning, it will all be okay. Now, you might be asking, what do all of these different things even have to do with a gradient? You haven't even told me what it is yet. Well, don't worry, we're just about to get there. So a gradient, it's basically the rate of expansion or rate of change of the level curves of a function, or level surfaces if it's a 3D level surface, 2D level curve. It all basically depends, and you'll see why. So I like to visualize the gradient in two different ways. The first being, we're going to look at the level curves of a paraboloid. Hopefully I'm saying that correctly. Okay, I'm going to go through this now, the first use case in which we're going to plot the level curves or XY traces of the paraboloid. And I'm going to put this on the screen so that's easier, but I'm just going to look at my screen so I kind of can explain it a little bit better. Okay, so basically we're going to look at the different XY traces, as I've said before. But the way that we look at that is when we're basically taking a snapshot of the function for every outputted z that it has. As you can see for this function, the paraboloid, the x squared plus y squared that I've detailed earlier, it's not going to have any outputs when, let's say that when the output is in the negatives, right? Because x squared plus y squared is always going to be positive and above the negative z. So we'll see that as we increase and we start at 0, that means that now we have our first, point. It would be a little point right there at the origin. But now as we increase, we're starting to see how our function is growing outward. It shows the growth of the function as, it has a specific output. If we look at the different level curves of the surface, we see that as it grows, it's going to radiate outward. So if we plot this as a function from 0, we know that if we start the vector of the gradient at 0, and let's say we're going across the x-axis, it's going to grow outward, as I'm showing you with my mouse. It's going to grow. And also, a special thanks for Sarah Helson. Harrelson, I think I'm saying that name right, for making this GeoGebra 3D graph. It's very helpful, to help you visualize the 2D trace. But now let's look at the 3D trace. For this function that we're going to look at now, it is now a 4D function. That means its inputs are x, y, and z. Well, we can't really graph a 4D function, right? Because we don't even know what the fourth dimension looks like. But we can graph the 3D surfaces or level surfaces of the function at given points in time. Just like with the last example, we're going to look at different snapshots in respect to time, or different snapshots in respect to the output. We're going to look at the level traces for this function. X squared plus y squared plus z squared, and we can say the output is f of x, y, and z, right? But we can also call that, we can just denote it with a different name, let's say w. But basically, we'll look at when the function's output is 0, we know that it's just going to be a point on the 3D field, because 0 is equal to x squared plus y squared plus z squared. We know that that's just going to be an infinitesimally small point with radius of 0. Now, when we go to, let's say w is equal to 4, we now have a sphere of radius 2. So you see how this is different from our last example? Instead of being a circle that's growing radially outward, it's going to be a sphere that grows outward. Now let's set w is equal to 9. Now 16. We can do this forever, but we can see that as the function expands, it is going to have a gradient that is now not 2D, but it's going to be a 3D gradient. So we can see this in a different function. So now that we know that this is how the function expands, let's look at it in a different aspect. Now we're going to look at the gradient on a real application or a real problem. Okay, so now we're going to look at an example. This function is animated by my friend Sana. If you can see, now we have this vector right here. This vector basically is the gradient of the function. As you can see, it follows the level surfaces of the function as it expands radially outward as a 3D gradient. Except we're only showing the gradient at a specific point on this constraint, which the constraint is that little blue circle that's on a little angle. As we can see, when we animate the function, the gradient follows the curve, and we can see that if we plotted all the gradients at the same time, it would expand outward in all directions away from the origin at the same amount. But we know that also the gradient is comprised of the partial differential in respect to x and y. Basically, when we add up the different components of the partial differentials, the x, y's, and z's for this case, we would have a resultant vector that points outward of the surface. We can see that on this function, the gradient is directly perpendicular to the surface. And what else does a gradient show us? Well, it showcases how the gradient basically helps us visualize the maximum rate of increase or decrease of a function. For instance, right now it's showing us the maximum rate of increase for the function, as if the level curves, let's go back to that example, if the level curves start from 0 and they radiate outward, that means that the maximum level of increase for the function would radiate outward, like in this example. It would radiate from the origin. But the maximum level of decrease would be basically just the negative of this, right? The vector would point inward, and it would show the decompression of the function as the function goes from, a big sphere, or the level surface of the 4D function goes from a big sphere to a singular infinitesimally small point. So, what did we learn thus far? Basically, we learned that the gradient is when we take the partial differentials in respect to every independent variable of the function, and it showcases the rate of expansion or rate of maximum increase or decrease of expansion for the function. Now, what is one thing that we can use the gradient for? Well, we can't just use the gradient for locating the maximum rates of increase or decrease of a function, even though that is useful. We can also use it to find critical points. Now, that is something I know that everyone finds useful. But let's go back to Calc 1 to make sure that our understanding of critical points is solid. So, a critical point on a function is basically where the derivative of the function, the first derivative of a function, is equal to 0, or it does not exist. These points help us locate where a function is turning around, has a maximum, absolute, local, maximum, or minimum, or a spot on the function where the tangent line does not exist. For instance, that could be where the tangent line is undefined, or where it does not exist. In Calc 3, this would kind of be the same thing. We would find a critical point where the gradient the partial differentials of the function are all equal to 0. Also, we would know that the critical point of a function is where at least one of the partial differentials does not exist at a certain point. Okay, so that is one instance of a function. We can find the critical points for a function if it's like, not constrained by any given amount. And let's say that if we have a function increasing for infinity, like the paraboloid, we're going to know that it doesn't have a maximum, but it does have a minimum, specifically at its vertex. Well, a vertex when it's increasing to infinity, or maximum when it's decreasing to negative infinity. But for a lot of functions, they're not going to have naturally a maximum or a minimum. But a bunch of functions will not have a maximum or minimum when they're just, set free to, do whatever they want on the graph. But when they're constrained, then we're going to know that where the constraint and the surface intersect, then there might be a point where there's a maximum or minimum of the function. Okay, so how do you think we'll find these critical points when we're given a function and a constraint function? Are we going to A, do nothing, B, make some tea, C, guess and check, or D, use gradients? What do you guys think? The answer is that it is D, with a little bit of C. Let's figure out why. Now, we're going to go into a very influential aspect of gradients, known as the Lagrange multiplier, or Lagrange multiplier. I like to say Lagrange, even though it's actually pronounced Lagrange, because it just sounds a little bit more fancy. So, to find the critical points of a function and its constraint, we will first find the gradients of the regular function, and then the gradient of the regular function, and then the gradient of the constraint. But you might ask, why do we need to know the gradient of the constraint? Well, it's because we know already that the gradients, since they showcase the maximum or minimum, the maximum increase or maximum decrease of a function, we know that when they're parallel to each other, meaning that the gradient of the function and the constraint are parallel to each other, that means that we know that both of the functions have a maximum increase amount or a maximum decrease amount. This would correspond to, respectively, a maximum point, a local maximum point, or a local minimum point. We know that this will only find the critical points for a function because if they're not parallel to each other, then the equation, the gradient times the derivative, is not equal to 0. Because we know that when the gradient times the derivative is equal to 0, then the surface and the normal or gradient is not orthogonal to each other, meaning that the level curves do not intersect. Let's look at an example. On the graph, we see A, our base function, which is z is equal to x squared plus y squared plus 2. And we see our constraint. Our constraint is a function x squared plus xy plus y squared minus 4 is equal to 0. We see this intersection as this. Our intersection path is basically two different functions. They're quite complicated to say out loud, so I'm not going to say them, but you can see on my screen. We see that with these two intersection graphs, there is going to be two minimums and two maximums. Thus, when we look at the level curves of the function from top down, we see that, like before, the paraboloid starts with a smaller circle and goes to a bigger circle. And we can also see that these level curves will eventually touch. Basically, they will come into contact with the constraint function. And if we look at that from above, it will show us that the level curves both form a tangential gradient. And when we look at that from the top, we see that the level curves just touch each other, meaning that the level curves intersect our constraint. And of course, that means that our gradients are parallel to each other and either showcase a maximum or a minimum. However, finding the Lagrange multiplier is oftentimes tricky and requires a lot of examples to get you to really understand how to do it, what it entails, and how to find the answer on your own. So, because that is a lot for this episode to go into, and I don't want this episode becoming too long, let me know if you want another episode detailing how to specifically find the Lagrange multipliers. With that, that is all I have for today's episode. I'm sorry for my voice. Hopefully it was not too bad for this episode, but I hope you enjoyed learning about gradients and their applications. Anyways, I hope you guys stay safe, have a great rest of your day, and keep on learning. Learn STEM,